Okay, so thank you for organizing this workshop. And as an information theorist, I really appreciate, putting this type of event so that we can have more relaxed venue to have discussions. So, in the program, I was trying to give a talk titled Shannon Theory of Ergodic Sources and Channels. Then I saw that there were a couple lossy compression titles, so I just backed away and decided to talk about channel coding. So throughout everything will be channel coding, but typically, from where I'm coming from, channel coding is a more difficult problem. Okay, so if you know channel coding, then source coding will come out easily. Okay, and nothing much is really new here. I'm kind of rehashing what I did 10 years ago, but there is a new technique I learned a couple years ago, so I'm kind of trying to put together these two things. So you can think of the whole thing as a tutorial or lecture where you can actually learn some techniques. And I understand that there are many people who are working on quantum information theory, and quantum information theorists are not shy of dealing with something that is not computable at all. Okay, maybe you can compute it using your quantum computer, okay, but you are not unhappy getting something that is in the limit, so you'll see a lot of that here. Okay, so this is a Shannon model of point-to-point communication. There is some communication channel. There are 2 points or 2 parties who'd like to exchange information. Well, not exchange, actually communicate information from one side to the other. And Shannon came up with a mathematical model. Okay, look like this. Okay, so there is a message M, okay, which takes, say, k bits, and it is encoded into a code word, x of n, and then it's corrupted and received as yn, and we decode the noisy version to recover message S mid M hat, and the probability that M is different from M hat is probability vector, PE, and typically we assume that M is uniform random variable. Okay, so for practitioners, this is a baseband, picture of communication. So what Kwang Yue was talking about was more waveform channel. Here is what you get, if you are programming something on your iPhone. And the fundamental trade-off is between the rate of communication, k bits we are transmitting over n uses of the channel, and probability vector, the transmitted message is different from our estimate, and how many times you are going to use the channel, or the degrees of freedom. And this is a very difficult problem. The genius of Shannon is coming up with a solvable problem. Okay, so he let n free parameter arbitrary, and he required probability vector to be arbitrarily small, and then he looked at the threshold rate. So it looks like this. For small n, obviously if you increase your rate, then the optimal code will have larger and larger probability vector. But if you increase n, then there is a sharp threshold, okay, which you call capacity. And he characterized that for discrete memoryless channel, okay, which says the conditional probability of getting the output sequence given the input sequence factorizes as symbol by symbol conditional probabilities. For such discrete memoryless channels, this threshold capacity is a single letter expression, which is mutual information between single letter input, just one symbol here, output y, and obviously the channel prescribes only conditional probability, so you have the freedom to choose your input distribution, and you can take the maximum input distribution, which fully specifies the joint distribution between x and y, and then maximum mutual information, which is purely mathematical quantity, is actually the physical threshold we are talking about. Good. So let's go through the proof. Okay, and this proof will be actually new to many of you. And once you see this, you'll probably never have to go back to typicality. And Kwang Yu, you may simplify your proof quite a bit. Okay, so we generate a random codebook. Codebook is a set of code words, say xn, indexed by your message m, and I'm going to use the notation nr. It was k before. Nr means n times number of transmissions times number of bits per transmission. So it's how many bits you are transmitting. And we are going to generate these code words individually I.I.D. Okay, according to I.I.D. distribution. Right? So this is how we generate it. To transmit message M, then we pick a code word that corresponds to that particular M, transmit it. Once you receive Y, okay, then for that fixed code word, we know what the optimal decoding rule is. We have to find M hat, which is called maximum posteriori probability estimate, as a function of output that maximizes the posterior distribution. Okay, but because the messages are uniformly distributed, that is proportional to likelihood, which factorizes as this, because it's discrete memoryless channel. But for any channel up to this point is the same. Map is optimal, which is same as maximum likelihood. But this is very cumbersome to deal with. So here is an alternative, which you call randomized likelihood decoding, or sometimes people just call it likelihood decoding. Instead of picking the right M, we simply draw M hat. Now it's capital, which means it's random. M hat according to the posterior distribution. Okay, so it's obviously suboptimal. And this was introduced by Yasei, RF, and Gohari in ISIT paper. It was award-winning paper that year. And they actually introduced it as a proof device. And here is why it will be a good proof device. I'm going to explain it in the next slide. But basically, this posterior distribution can be written as 2 to the something that looks like mutual information, okay, which some people may call information density. Okay, so it's what you take expectation for to get mutual information. Okay, and this posterior can be related to this information density that way. And in the next slide, we are going to deal with this object. So that's how it is historically introduced. But then, several years ago, I met Polkov, and he realized that this is actually not a bad decoding method at all. Because if you sample correctly from the posterior, then the probability of error you are getting is, at most twice, the optimal probability of error. Okay, so that's pretty nice, because typically for channel coding people, they talk about 10 to the minus 4, 5, 6, twice that, which is still small. For actual communication engineers, they talk about 10 to the minus 1, so they may be a little bit unhappy, but that's okay. Right? And there are actually many variations. I mean, for example, here we do it for block error probability. You can actually do it for bit error probability as well. You get the same answer. Many different results. If you take multiple samples, 3 samples, then you can make it 1.5, you know, so on and so forth. Okay, and it may actually imply some practical decoding technique, okay, which goes back to Ralph O'Neill in 2001. If you look at Mazar Montanari textbook, they again deal with it. And neither team seem to realize that it is actually a good decoding method, so they kind of stopped short. Recently, we also explored, you know, what we can do about it. But that is not the point of this talk. We actually want to prove something so that we can go beyond I.I.D. So suppose m equal to 1 is sent, okay? Then now I'm gonna, yes?
Is the proof of Kauf's lemma easy?
Oh yes, yeah, very, very easy. Yeah.
Can you tell us a little bit about it?
Oh yes. So suppose, you know, I mean, actually maximum map decoding is a simple thing. Suppose you go to a multiple choice exam, okay, and you know that answer A has the highest probability. Okay, then which answer you are gonna choose? Of course, answer A, because it has the highest probability, so it minimizes the probability better. Okay. So now instead you actually draw your answer according to the distribution. Okay, it's like the rolling a die, okay, in an exam. Then what is the probability that your random roll will be exactly same as the true answer? Okay, so let's call one as x, the other as x prime. The probability that x is equal to x prime can be upper bounded by, for any value a, probability x is equal to a, okay, plus probability x prime is equal to a for any a. Okay, and therefore you actually, or actually, I should say, not equal. Okay, anyway. So probability that x is not equal to x prime is upper bounded by either x is not a or x prime is not a, and therefore that is twice probability x is not equal to a, take any a, and in fact we can take the maximum a. Okay, so that's how you prove it. And Kover and Hart use it to prove their celebrated machine learning result, okay, in nearest neighbor classifier, which is, by the way, all from electrical engineering, not from computer science. So anyway, okay, let's go back to simple probability of decoding error analysis. So I assume that m is equal to 1 was sent. And then I'd like to look at the probability that m hat is not equal to 1. Okay? And I'm going to compute this probability, but I'm going to condition it in multiple times with different conditions. First, I'm going to assume that output is fixed, codebook is fixed. Still, there is a probability of error, which is non-trivial because I'm randomly choosing my output. And recall that I'm choosing the posterior sampling. So therefore, the probability of error is exactly the probability I sum this over anything but 1. Okay? And then I simply just drop one term from the bottom, so I have an upper bound. Okay, so that is step 1. Step 2, since y and the true code word are independent of any wrong code word, so suppose I average out all the other code words, okay, and let's look at what happens to this 2 to the information density. Well, the marginal distribution is the same, and therefore if you average the conditional distribution with respect to the marginal, then the numerator becomes P of yn, denominator is P of yn, and therefore it becomes 1. Okay, so if we apply average out of all wrong code words, then what you get here is there are 2 to the nr minus 1 terms, so we get this. And at this point, you are very much tempted to use Jensen's inequality to finish the proof, but actually it's the wrong direction. So all we need is concentration. And let me remind you again, I was not defining typicality, nothing. Okay? Decoding was very natural. Typicality happens only here. All I need is concentration of this information density. Okay, and I need just one side, okay, which was stressed multiple times by Sergio Verdiu in many of his lectures. So by law of large numbers, this information density is with high probability above ni minus epsilon. Okay, therefore, either it is less than that, okay, or it is greater with high probability. Okay, and then you take care of the small terms, and you have the coding theorem.
Johan,
Yes.
how different is this approach from the so-called information spectrum method by Untitled? Are they the same, or?
I mean, broadly speaking, but I don't think they use randomized likelihood decoding. Closest to this proof argument is actually Yasei's original paper, but I mean, this is probably a little bit simplified. So we need only 3 lines, maybe 4 lines. But I'm not going to teach it in my class. The reason is already random coding itself is quite complicated. Now you are talking about double randomization, and I mean, these students will completely get lost. Okay? But among experts, I think this is the right proof. All right. So this was for I.I.D. And again, let me stress, there was nothing really I.I.D. about it. I mean, up to this point, everything was just for any one-shot communication. The only I.I.D. NIST I was using was law of large numbers. And you can see where I'm going. So first, let's think about the channel. I mean, what is the right extension of beyond I.I.D.? So here is a discrete memory list channel. Again, we have the input-output conditional probability, and we are using this channel over and over again. And defining channel is a cultural war. Okay, I mean, you can actually lose your friends trying to define channel. Okay, you can upset a lot of people. I once upset Jim Massey. Okay, but here is my view, and I think actually this view will be appealing to many of you because you are physicists to some extent. And here is what we call functional representation lemma. So any conditional probability of y given x can be represented as a function of x and some exogenous randomness z, which is independent of input with some cardinality bound. Okay. So with this picture now, I think of this discrete memoryless channel as the following. We have some function, discrete input x, discrete input z, symbol by symbol function of 2 arguments, and this z is I.I.D. Any channel we think about can be viewed this way. Okay, feedback, non-feedback doesn't really matter. All we care about is just messages independent of the noise. I'm not going to force you to take this as the right model of DMC, but I'm going to use this. And then the natural extension is just replace I.I.D. with stationary ergodic. Okay, so same model, symbol by symbol mapping, okay, with input and noise has memory. And here is what we are going to prove in today's lecture. Capacity is in the limit of maximum mutual information, normalizing mutual information between the input and output. And for this particular channel model, it is very nice that this mutual information is super additive. Okay, so therefore, limit can be replaced by supremum. And therefore, what I'm going to do is I'm actually going to prove that this normalized mutual information is achievable for every n. Okay, then we are done. I mean, converse is always very easy for this type of problem, so I'm not going to deal with it. Okay, and to prove this, we are actually going to review ergodic theory a little bit. Okay, and there will be a bunch of quizzes. You have to answer that. And the technique we are going to use in the end is Gallagher's coding technique. So everything goes back to Gallagher's 1968 textbook. But I stole it and use it for the channel coding problem. Okay, so let's start with something very simple, stationary. Okay, and everything I'm doing is actually random process viewpoint. Okay, because ergodic theory, I mean, if you talk to real ergodic theorists, they always talk about billiard balls, you know, I mean, all this dynamical system stuff, which I don't really understand. So I'm just doing it for electrical engineers. So we have a random process on finite alphabet, which you all understand. And I'm going to define probability space induced by this random process. Okay, so omega is the space of just realization, infinite sequence. Sigma algebra is just induced by this infinite sequence of random variables. Okay, and probability, I mean, we already assume we know probability. And in this picture now, xn of omega is simply omega n, the nth coordinate. And we are going to define time shift operator from omega to omega, which is simply shifting time. Okay, and in this picture now you can also think of xn of omega not just as nth coordinate of omega. You are simply applying the time shift operator n-1 times and then take the first coordinate. Okay, so that is our time shift. And we say x is stationary if for every event the inverse image of that event, probability, is same as the probability of event itself. And the reason we are doing the inverse image, not t, is because we are using the one-sided random process. If it was two-sided, then it will be actually the same. So that is stationary process, and we are going to assume throughout everything is stationary. Now ergot is t. We are going to say an event is shift invariant if you do the inverse time shift, then you stay the same.
There's some noise channel in that sign.
I'll speak up. Okay, and you can easily see this is actually in the tail sigma algebra, because if you shift it, it should be still the same. So you don't really have to think about what happens right now. It's in the remote future. Okay, and now we say a random process is ergodic if for every shift invariant event, the probability is trivial. It's either 0 or 1. It's always very unintuitive to think about the definition. It's probably easier to understand what's going on by a property of ergodic processes, and that is Birkhoff's pointwise ergodic theorem. So for stationary ergodic process with finite L1 norm, if you take time average, then it converges to the ensemble average with probability 1. Okay, so this we know. And there is a related concept which we are going to use very briefly. Shannon-Macmillan-Bryman theorem shows that for stationary ergodic process, discrete or finite alphabet, if you look at normalized log probability, then it converges to entropy rate, which is defined as normalized log entropy. And again, this convergence is almost sure, thanks to Bryman. Any question on stationarity and ergodicity? Yes?
If you remove stationarity, could you just work with conditional expectations over the tail algebra?
I mean, you know, stationarity is not really something important. I mean, suppose that you just make x1 behave very differently from the rest. Then process is clearly not stationary, but you may still have ergodic behavior.
There's this canonical tail algebra. You could do everything conditioned over the tail algebra. The tail algebra is this S.
Yes, yeah, yeah. So ergodicity can be separated from stationarity, but I mean, for me, it's, you know, and there are actually textbooks that do that, but I mean, for us, simpler is the better. Okay. I mean, there are, I mean, different notions, you know, asymptotic mean stationarity, you know, I mean, all different notions, you know, people dealt with, but, you know, we'll stay simple. Any other question? All right. Okay, so ergodic or not. Suppose that you have I.I.D sequence and form a random process out of it. It is ergodic? Come on. Yes, yeah. So how do you prove it? I mean, because it's in tail sigma algebra by Kolmogorov 0-1 law, it should be trivial. And now suppose that we draw theta, the bias of coin flip, uniformly at random, and then draw coin flips conditionally, I.I.D, given the theta. So now you have a mixture of I.I.D. Is this ergodic? Obviously it is not, okay, because if you look at this event, okay, the long-term average, which is shift invariant, okay, and then that probability of the event is not 0 or 1, okay, therefore it is not ergodic under our definition. And this is not actually a very unique example. We can actually show that for every stationary process, it can be decomposed into many different ergodic modes, just like this one. Here, each theta denotes the ergodic mode. So you actually have a bunch of ergodic processes mixed together by theta. And any stationary process has this feature. Let's move on to something more interesting. Suppose we have the simplest ergodic process. So it goes like this. The process is with half probability 0, 1, 0, 1, 0, 1. With another half probability, it is 1, 0, 1, 0, 1, 0. Okay? So just two sequences. It is stationary, right? If you look at any time, they look the same in distribution. Okay? It is ergodic, okay? Because to be shift invariant, you should take either the empty set or the whole set, because they ping-pong each other. Right? So this is one example you have to keep in mind to understand a couple of counterexamples. So now suppose X is stationary ergodic and y is symbol by symbol function of x. Is y stationary ergodic? Yes, it is. And in fact, you don't have to actually take a symbol function. You can take a far more general function. As long as you are sliding your time in the right manner, okay, then y is stationary ergodic. Okay, so how about the following? Suppose now you have two independent ergodic processes. In particular, I'm going to take x and z to be independent copies of w. And I'm going to take y as a very simple function, both two sum of x and y, symbol by symbol. Okay, so previously, a function of a single ergodic, and now we have a function of two ergodic processes. Is this y ergodic? Well, Yanis mentioned during his talk, we need some condition when we are dealing with multiple ergodic processes. And in this particular case, probability that y is 0, 0, 0, 0, 0 is exactly when x and z are the same. And that happens with same half probability. But when you have this type of constant sequence, this is shift invariant, and therefore y cannot be ergodic. And this also implies that z and x and z are not jointly ergodic, even though they are individually ergodic.
Independent.
But here is a kind of patch for this type of negative result. Suppose you have a symbol by symbol function, and again, this function can be something more general. Suppose one of them is mixing fast, say I.I.D, okay, and the other is arbitrary stationary ergodic, then this y is stationary ergodic. So this is one thing we are going to use later. Okay, and now based on what we have seen so far, let's attempt at the proof for n equal to 1. Again, the setting is we have symbol by symbol mapping with input and noise. Noise is stationary ergodic, arbitrary. We are going to do the random coding as before. We are going to fix px or px1, take I.I.D over time, I.I.D over code words. That is our code book. And now, from what we just argued, x is I.I.D and z is arbitrary stationary ergodic, and therefore x, z, y, the whole thing should be again jointly stationary ergodic, right? I mean, I'm actually taking x, z, identity function plus y as the whole function. Okay, so they are all jointly stationary ergodic. Okay, and now I'm going to use randomized likelihood decoding. Okay, the same thing, and all you have to care about is concentration of this object, information density. Okay, and what can you use? We can actually use Shannon-Macmillan-Breiman theorem, okay, which argues that when x and y are jointly ergodic, then all their entropies, individual entropies, joint entropies, will converge it to the right limit or average, and therefore we have this convergence. And this shows that any rate that is less than 1 over n of ixn yn is achievable for this particular co-distribution, and in particular by superadditivity, this single letter I of x1, y1 is achievable. Any rate less than this is obviously less than this, so therefore any rate less than single letter mutual information is achievable. Okay, so next time when you have a choice of getting I.I.D noise versus stationary ergodic noise with the same marginal distribution, you should always choose stationary ergodic noise. You can at least do as well as memoryless noise. All right, so that's fine. Now we want to generalize this to 2, 3, 4, so on and so forth. So let's see whether we can do it. So suppose that you have stationary ergodic x And now I'm going to block them 2 by 2. 1, 2, 3, 4, 5, 6, so on and so forth. Is this ergodic? It is actually not. And again, let's go back to our W example. For W, if you block them 2 by 2, then you have constant sequence. 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, each happening with half probability, and therefore it has 2 ergodic modes. In fact, there is a definition called total ergodicity, which says that if you take any n block for any finite n, and each block process is ergodic, then it is called totally ergodic process. Here is a more general picture. Suppose you are taking n blocks, okay, then it is actually a mixture of k ergodic modes where k divides n. For example, in this case, if you do 2 for W, there are 2 ergodic modes. What about 3? If you take blocks of 3, then what do you expect? 3 ergodic modes? No, there is actually a single ergodic mode for 3. If you take blocks of 4, then how many ergodic modes? There are only 2 ergodic modes, so on and so forth. Okay, so there is some k that divides n such that your process, the block process, is mixture of that k different ergodic modes. And what's even more beautiful is if you actually shift by little amount, okay, do it n times or k times, then you go over all different ergodic modes. Okay, so this is one ergodic mode, this is a second ergodic mode, then you go back to the first one, and you go back to the next one. And if you look at all of them, okay, then they actually are ergodic because they are sliding window. Okay, so we are going to use this. Okay, but now we have seen total ergodicity, so why don't you just use it briefly? Okay, so suppose we do the n block coding, and we are going to assume now that the noise is totally ergodic. Okay. Then now, if you look at the block process, they are jointly ergodic, and so is the output. So therefore, if you use the randomized likelihood decoding for codes that is defined on the n ladder for capital N length, then we can use what we had before. Okay, so NR is less than this. The n ladders, mutual information, just using our n equal to 1 result. And this is achievable. Okay, so here's a recap. We looked at the ergodic noise channel. Okay, good thing is by using random coding, randomized likelihood decoding, and Shannon-Macmillan-Breiman theorem, we actually could prove achievability in a fairly straightforward manner. What is really bad is this works only for total ergodicity. That is not what we promised at the beginning. And what is ugly, if you have noticed, is that even though we actually need just this, we need n-ladder mutual information achievability, what we are actually proving is something far more. Okay? There is a mismatch between the block size. We are actually doing the super block coding. And what we are showing is this is achievable for I.I.D. distribution. So that is ugly. Okay? So we need a new technique, and here is what we are going to do for the remaining time. Let's visit n equal to 1. Everything is the same. Encoding is the same. Random coding I.I.D. Okay? And again, everything is jointly ergodic, so we could use Shannon-Macmillan-Breiman theorem, but we are not going to do that. We are actually going to do randomized decoding, but not from the posterior, but we are going to sample it from another distribution, okay, which is coming from the product of the marginals, one ladder marginals. Okay, one thing you can easily check is because of the I.I.D. codebook we are using, this 2 to the I quantity is actually 1 as before. So every step we are using, the 3 steps we are using for I.I.D. case follows. For the last step, now we can use Birkhoff's ergodic theorem because we have simply just a sum of single letter quantities. Okay, so this shows achievability without any nuisance of n letter. We just prove n equal to 1 and we get n equal to 1. And now extension to n equal to 2. We are going to use, arbitrary n. We are now going to use the n letter coding as before. But the trouble is, if you look at the z sequence, it is not ergodic. But here is a beautiful idea by Gallagher. Why don't you just use the first part starting at ergodic mode 1 and second part ergodic mode 2? How do you do it? Just skip one step. Then overall, we are going through all ergodic modes. Okay, so if each block is length n, capital N, each letter is small n, each block is capital N, then we are repeating that capital N block n times so that we go through all ergodic modes uniformly by skipping ones here, here, and so on. Then the whole sequence now behaves completely in an ergodic manner. Okay, and we are going to do the randomized decoding where every index is understood by ignoring the skipping positions. And again, by Birkhoff's ergodic theorem, we actually have the desired result. Okay, so let me conclude the talk. I introduced 2 Shannon theoretic tools, which is not widely known. One was randomized decoding, either from the true posterior or the product of the marginals. They are extremely powerful. You don't need to assume anything. And analysis, again, among experts, can be very, very simple. And I think everything should be really proved this way once you get used to it. And second thing is Gallagher's ergodization technique. Okay, so basically, whenever you have ergodic process, and if you want to do the blocking, then you just skip things around so that you go through all ergodic modes. This is, again, a very powerful tool. Okay, and for some reason, I'm not sure all this, one-shot achievability business people haven't exploited that. So it'll be some interesting technique to explore, try to get some of these, second-order methods, so on and so forth. If you really want to go beyond I.I.D. And there are several extensions and related results. First, everything we are doing so far actually didn't require the input memory to be 1. As long as we have the functional relationship, everything goes through, so we can actually introduce input memory with no problem. How about feedback? Well, feedback problem is actually no different from no feedback problem, as long as you can identify some mapping that is connecting the virtual input U to the output. Okay, and your input is really just tunneling your virtual input through some mapping. Okay, so every feedback problem can be made into non-feedback problem in one-to-one manner if you deal with mutual information. If you are dealing with information density, then it's a different story. So as long as you have a working channel coding theorem, then the problem is essentially solved. You don't really have to work on feedback anymore for discrete time. Finite state channel, again, there are a bunch of results, non-feedback for Gallagher, feedback for Tatikonda Mitter, Permuter, Weissman, Goldsmith, and these results can be proved in our way. Okay, and also, there are many sophisticated ergodic channel models. So if you look at Bob Gray's monograph, then there are many different models which may not be covered by this, but who knows? This technique might be useful. And finally, this is the source coding part of this talk. For lossy compression with ergodic source, you can again do the same thing. You have to do the blocking, and then you just skip letters so that overall everything looks like ergodic. So for feedback result, it goes back to Gallagher and Berger's 1971 rate distortion theory textbook deals with it a little bit, but he is dealing with total ergodicity. And Ramji, for his PhD work, worked on the feed-forward version, which is a dual-to-feedback version of this. Okay, so I think some of those techniques might be applicable to a feed-forward case as well. So here are some references, and let me stop here. Thank you.
So Johan, so what do you mean by if you consider if you resolve the problem for non-feedback channel, then you don't have to consider feedback channel? Is that what you say?
So this is a purely algebraic relationship. Whenever you have conditional probability, I mean here it is the causal conditioning, but it can be viewed as a conditional probabilities. Then you can always write it in a functional form like this, and rewrite everything as just regular mutual information between some virtual input u and y. And now if you look at the form of this one, that is exactly same as the form I wrote above.
But this one can be difficult to compute, is that right?
I mean, computation is a different issue. I mean, you know, when we talk about multilateral expressions, we are just giving up the computation side.
Oh, okay.
I'm just talking about the proof of, achievability proof of a coding theorem. And in terms of coding theorem proof, we don't really have to do anything. It's just purely algebraic manipulation. We just reuse the non-feedback coding theorem to prove feedback coding theorem. And computation is a completely different issue. I mean, it's actually far more interesting question, but for general channel, I don't know whether we can really have a good massage for this type of multilateral expression. But I think quantum information theorists are so used to it, so I don't think they care a lot. Is it correct, Andrea?
I think it's coffee time, so maybe we should thank both the speakers of this session and keep our questions for them during coffee.